All right, let's get started. So today, I just want to go through a couple examples on variation of parameters because I don't know if they're going to be on the exam. I have a feeling that this concept might be on the exam, just so that we are prepared. Variation of parameters. By Thursday, I will have actually the coverage for the exam. I'm sure Professor Gibson will tell you, but just in case, parameters. So this is just a new technique like the undetermined coefficients. It's being used a lot to solve non-homogeneous differential equations, in particular the second order, like ay double prime plus by prime plus cy equals f of x. If you remember that if f of x is something like e to the ax, or a linear function ax plus b, or ax squared plus bx plus c, or even like a higher power polynomial functions, or if we have a cosine omega x and sine omega x. If f of x is any of those, we could try to use undetermined coefficients. So can use undetermined coefficients, or even like a sum of those functions or product of those functions, we can try to use that. But sometimes you have f of x that's not so simple, right? It's f of x might be complex, a different kind of functions. Then this undetermined coefficients doesn't really work well. So that's why we need variation of parameters as a second technique. So if f of x is complicated, then we can try to use variation of parameters. So the process of using it is basically the same thing as the undetermined coefficients. It's just that in part of it, when we find the particular solution, it's a little bit different process. So the first thing we're going to do is we're still going to find the homogeneous solution. In the middle of that, you might find two base solutions. So with base solutions that are y1 and y2, the homogeneous solution is just going to be some constant c1, y1 plus c2 times y2. So note that c1 and the c2 are constants. So we have seen that before, there's nothing new. So the second step, when we find the particular solution, instead of guess the particular solution based on f of x, so what we're going to do, we're going to use a general formula for particular solution. So yp equals u1 times y1 plus u2 times y2. And this general formula for particular solution has u1 and the u2 are functions of x. They're not necessarily constants. So that's something to watch out for. So how do we find the particular solution? We're not going to find the derivative. Remember that if we use the undetermined coefficient, we find the derivative, right? We get a particular solution, we find the derivative, we put it into the differential equation. When we find a particular solution in this technique, we're not going to find the derivative to put in there because we don't know the derivative of u1, u2, or the second derivative, so that wouldn't work. But there's a condition that we could apply. So we're going to require that two conditions. The first one is that u1 prime times y1 plus u2 prime times y2, that has to be 0. That's the first condition we can use. We don't need to show any work to derive it. We just, I would say just memorize it and then use it. and then u1 prime times y1 prime plus u2 prime times y2 prime equals f of x. So those are the two conditions that we could use. Assuming that we solve for the homogeneous solutions already, so we have y1 and y2, we can definitely take the derivative of them to get y1 prime, y2 prime. So the only thing we don't know here is the u1 prime and u2 prime. In the second equation is the same thing, u1 prime, u2 prime. So we have derivatives in both equations for use. So that's what we're going to use. We're going to use those two equations to solve for the u1 prime and the u2 prime from the two equations. And after we've done that, since what we found are actually the derivatives of u1, u2, so the next step is we have to integrate to find u1 and the u2. And after we find u1, u2, if you recall that the particular solution is a u1 times y1 plus u2 times y2, so we could take what we found, put it there to find the particular solution. Find y particular. And then the last step is just like always, so we're going to find the general solution by using the homogeneous solution plus the particular. I would say that if you kind of review what we did, the process of finding the particular solution is different compared to the undetermined coefficients. But you still need to find the homogeneous solution. You still need to write down the general solution at the very end. And then we're going to look at a couple examples to kind of practice on this. One thing I want to point out is that this technique doesn't have to be for, we don't have to use it for only complex differential equations with complex f of x. It could work with any equation that we apply this method. Even if f of x is simple, we can still use this approach to find a particular solution. So here's an example. So the first example is that we're going to solve finding the general solution, y double prime minus 3y prime plus 2y equals e to the 3x. This is something we have seen before, because this is the simple f of x. We can use undetermined coefficients if we want to. Y equals a, so we're going to guess the particular solution, y equals a e to the 3x, and then solve for a from there. But that's not what we're going to do. If you want practice, I really recommend doing that. So what we're going to do is we're going to use variation of parameters. We should end up with exactly the same answer at the end for a particular solution. So the first thing I'm going to do is I'm going to find the homogeneous solution, which we're using e to the ansatz e to the lambda x, put in there, find the characteristic equation, solve for lambda, and then write down the base solution, write down the homogeneous solution. So I'm just going to write down the base solution. I'm going to skip some work. So y1 will be e to the x, y2 is equal to e to the 2x. Therefore, the homogeneous solution is going to be c1 e to the x plus c2 e to the 2x. So like I said, I'm skipping quite a bit of work there to find the homogeneous solution. Is that okay? It's if you don't feel comfortable, it will be some practice for you to work out the process. And then the next step is that we're going to find the particular solution using the following process. So I'm going to write down the general formula first. So y particular equals u1 y1 plus u2 y2. You don't have to plug in y1 y2 now. So y1 and y2 are the two base solutions we found when we find the homogeneous solution. You don't have to plug them in here, but I like to plug them in so that I know how far I go in the process. Like I said, you can just leave it the way it is and come back to this later, but I like to plug in y1 and y2. So u1 e to the x plus u2 e to the 2x. And I cannot go further because I don't have u1 and u2. So I'm going to leave it, and I'll come back to this step. And then the next step is to actually find the u1, u2. Instead of taking the derivatives of y particular, like we did before, we're not going to do that. We're just going to kind of skip ahead using the two conditions we had earlier. So if you remember that here we have those two equations we have to satisfy. So let me write them down again on the side to remind us. So we have u1 prime y1 plus u2 prime y2 equals 0. u1 prime y1 prime plus u2 prime y2 prime equals f of x. At the beginning, it's good to just kind of write it a few times, but as you get more comfortable, you have it memorized, you don't have to write them down. So now I'm going to plug in the y1, y2, the y1 prime, y2 prime, and f of x. So I have u1 prime times y1, which is e to the x, plus u2 prime times y2, e to the 2x, must equal 0. Then I have u1 prime, y1 prime. So when I write down the second equation, I have to take the derivative of the y1 there. So this is the y1, but I take the derivative of e to the x. Happens to be the same. E to the x plus u2 prime times derivative of e to the 2x, that's a 2 e to the 2x, equals f of x. If you remember that f of x from the beginning, it's e to the 3x. So this is the two equations I have. And then you just have to remind yourself that e to the x is the coefficient because we're solving for u1 prime and u2 prime. So e to the x is a coefficient, and the e to the 2x is also a coefficient. Same thing with those two terms. So keep in mind that we're looking for those two terms, the u1 and u2 derivatives. So we treat them as variables. So if you remember solving system of equations, you can use elimination, substitution, or matrix equation. So I'm going to use elimination first because that's a little bit easier. I don't think I ever use substitution in solving those equations. So here, by looking at this, I have u1 prime e to the x, u1 prime e to the x are exactly the same. So if I take first equation minus the second one, then I get a 0 from those two terms. Or I take the second equation minus the first one. That's actually what I'm going to do. I'm going to use the second equation minus the first one because I get a positive on this side instead of a negative. So we're going to take the second equation minus the first equation. So like I said earlier, when I subtract, the first terms in both equations are identical, so when I subtract, I get a 0. The second terms in both equations, your first equation gives me 1 times u2 prime e to the 2x, but then the next equation gives me 2 times u2 prime e to the 2x. So if I take twice of this minus the first one, so I end up with 1. So that's a u2 prime e to the 2x. And then the right-hand side gives me just e to the 3x minus 0, e to the 3x. Any questions? And now we can actually solve for u2 prime. So divide by e to the 2x. So u2 prime equals e to the 3x divided by e to the 2x. And if you remember that when you divide two terms with the same base, we end up subtracting the exponents. So that's going to be e to the 3x minus 2x. That becomes e to the x. This is the u2 prime. And next step, we have to find out the u1 prime. So if you remember solving system of equations, after you find one, you have to plug into one of the equations, find the other one. So I'm going to use the first equation because I have a 0 on the right-hand side. It's easy to work with. So that will give me u1 prime e to the x plus u2 prime. I already solved for u2 prime, which is e to the x, times e to the 2x, which equals 0. Move the second term to the right, divide by e to the x, so I get u1 prime equals negative e to the x, e to the 2x, divide by e to the x equals negative e to the 2x. Remember that we're solving for the particular solution, right, which requires u1, u2. So far what we have is we have a derivative of u2 and a derivative of u1. Then we need to integrate each of them to figure out u1, u2. So u1 equals integral e to negative e to the 2x dx. And I'm just going to write down the answer because I'm sure you can integrate it. So that's a negative 1/2 e to the 2x. And u2 equals integral e to the x dx, which is just e to the x. So that's integrating. Will give us u1, u2. After we have them, we can now put into the particular solution. So y particular we had is u1 e to the x plus u2 e to the 2x. If you remember, that's what we had. So now we're going to plug in u1, u2. So that will give us u1, which is negative 1/2 e to the 2x times e to the x plus u2, which is e to the x times e to the 2x. So what I did is I take e to the x, put in there, and I take u1, put into there. And simplify, really. So here we have e to the 2x, e to the x, that's e to the 3x, multiplied by negative 1/2. We have e to the 3x times 1. So negative 1/2 plus 1 is positive 1/2. We get positive e to the 3x. Which, if we use the undetermined coefficients, by assuming yp equals a e to the 3x, we just end up with the same at the end. It's actually a lot faster that way. But as a practice, I just want to show you they give you the same at the end.
So when integrate the u, why do we not have a c?
we don't add a C because even if we have a, or do we have a C? Even if we have a C for this part plus a C, eventually let's just say we have let's say plus a C for this part, and well, plus C1 plus C2 for the n. And then when we multiply U1 with e to the x, we just end up with this extra term, C1 e to the x, which will be absorbed into the homogeneous solution at the end, which already have a C1 e to the x. That's the reason we don't add constant, because the constant times y1, the constant times y2 will be absorbed into the homogeneous solution. That's a good point. So no need to add C. It's just going to be absorbed. Any questions? And then at the end, don't forget to write down the general solution. Y general is equal to C1 e to the x plus C2 e to the 2x. Those are the homogeneous solution plus a particular solution, which is 1/2 e to the 3x. Any questions? So the process is very, I would say, like when you solve differential equation, the process is very important. Definitely worth to kind of pay attention to when you work on examples. If you don't have questions, I want to take the same example. Instead of solving it using elimination, at the beginning when we solve it using elimination, I want to use matrix and determinants. So the first thing I'm going to do is that I'm going to take this system of equation I had, and I'm going to rewrite it using matrix equation. So u1 prime, u2 prime, those are the variables, and the e to the x, e to the 2x, those are the coefficients. So in terms of matrix equation, if you remember what it means in algebra class before, matrix equation is, you read it like this: the coefficient goes into the coefficient matrix in the beginning, and the variables goes into the variable matrix, and the right hand side goes into a matrix. So the coefficients I'm going to put into the first matrix, so I get e to the x, e to the 2x, e to the x, and a 2 e to the 2x. So what I did is that I kind of picked. So that's the coefficient, that's the coefficient, those are the coefficients. So those 4 coefficients, I kind of place them in this 2 by 2 matrix. And then the variables begin with u1 prime and then u2 prime. So that's going to be a vertical matrix. u1 prime, u2 prime. The right hand side, I only have 2 times 0 e to the 3x, going to go into this matrix. So that's how you take a system of equations, convert it into a matrix equation. If you have more equations, you just kind of increase the size, or if you have more variables, increase the size of each matrix. So this is what we call this. Usually we call that A. It doesn't have to be A, just some coefficient matrix. And this variable matrix is, I'm going to call it capital X. And the right-hand side is just what we call the B matrix. So this is really AX equals B equation. How do we solve it using determinants? So to solve this, the first thing we need, the determinant of A, what we call Wronskian. So the Wronskian is defined as determinant of A, which is equal to, in this example, So Wronskian is sometimes used W. So that's written as W equals vertical line means determinant for matrix instead of brackets. So that's e to the x, e to the x, e to the 2x, 2 e to the 2x. And then to calculate that determinant, what we're going to use is called AD. So this is the element A, that's element B, that's C, that's D. So it's going to be AD minus BC. So this diagonal minus the forward diagonal. So backward minus forward. So AD minus BC. So that's going to be e to the x times 2 e to the 2x minus the other diagonal, e to the 2x times e to the x. It's always going to be a subtraction between, well, it has to be a subtraction, but it could be positive if we have a negative here. Have you seen this before? Okay, good. So let's just calculate what the Wronskian is. So that's going to be 2 e to the 3x minus e to the 3x, so that's going to be e to the 3x, which we're going to need. So that's the first part we need. The next part is that the first variable, in this case, u1 prime. So we're looking for two things, right? We need the u1 prime and the u2 prime. The first thing, the u1 prime, is going to be given by 1 over the Wronskian times the determinant of a new matrix. It's very important to get this new matrix right. And what's this new matrix? This new matrix that we're going to take the determinant of is the A matrix, but with the first column replaced. So what I meant is that we're going to take this A matrix and we're going to replace this first column with the right-hand side, the B matrix. So we're going to take 0 e to the 3x to replace the first column. So that's what's going to go into this matrix. So that will be 0 e to the 3x. Well, let me use a different color. 0 e to the 3x. And then the second column just stays the same. So e to the 2x, e2 e to the 2x. And this will tell us what the first variable is. And then we're going to plug in the Wronskian and calculate the determinant. So that's going to be 1 over e to the 3x times the determinant of this one is actually a lot easier to calculate because you always have a 0. So one of the diagonal will become 0. So in this case it's AD, so that's a 0 minus this diagonal. So 0 minus e to the 2x, e to the 3x. And if we simplify this at the end, 0, we don't have to write it, so that gives us a negative because this is minus 9. And then e to the 3x in the denominator, e to the 3x in the numerator, cancel give me 1, and I have e to the 2x remaining. So I just end up with negative e to the 2x. So that's a u1 prime. So that's to find the u1 prime. Any questions? I know that if you haven't seen this before, it could be confusing, but just keep in mind that if you try to use the determinant to solve for the variables, this is basically the formula right here. And if you want to use the formula, you have to know what the denominator is that's defined by the determinant of the coefficient matrix. To find the second variable, u2 prime, it's the same formula. It's going to be a 1 over w times the determinant of a matrix. And the second matrix is not the same as the first matrix. This second matrix is given by taking the A matrix again, but we're going to replace the second column with the right-hand side. The first column stays the way it is, it's just that the second column will be different. So the second column going to be replaced with 0 e to the 3x, but the first column is e to the x, e to the x. It doesn't change. And that will give us 1 over e to the 3x times, again, one of the diagonal will become 0, so that's e to the x, e to the 3x, minus the 0. That will be e to the x, e to the 3x, minus the 0, and eventually just give us e to the x. Any questions on that? So that just shows us a different way that we can use to find the u1 prime, the u2 prime. Sometimes it's a lot easier to use the determinants and then the matrix equation. Sometimes elimination works just fine. I just want to show you the different ways. You have to decide which one you prefer. Any questions? All right. Shall we do another example? We've got plenty of time. All right, let's look at another example, which is, again, we're just going to find the general solution for y double prime plus 3y prime plus 2y equals 1 over 1 plus e to the x. And so you can see that this is the f of x. It's not that simple. It's not one of the common functions we use for undetermined coefficients. So this one, we're going to use variation of parameters only. So don't use undetermined coefficients here. So we're going to use variation of parameters. So the first thing we need to find is we need to know the homogeneous solution. I'm just going to write down what I have to save a little bit of time. So y1 equals e to the negative x, y2 equals e to the negative 2x. So the homogeneous solution is going to be c1 e to the negative x plus c2 e to the negative 2x. Again, for practice, you might want to kind of work out the process if you're not familiar with the process. So the next thing is that to find the particular solution, so I'm going to write down the general formula. Yp equals u1 y1 plus u2 y2. So I'm going to plug in y1, y2. So that's u1 times e to the negative x plus u2 times e to the negative 2x. And we will come back to here to plug in u1 and the u2 at some point. But we also require the conditions Is it okay if I don't write down the general formula for the equation, just plug them in? Okay, so it's going to be u1 prime is always a derivative, so times the y1, which is e to the negative x, plus u2 prime times y2, e to the negative 2x, has to be 0. So I plug in y1 and a y2 there. And then the next equation is similar, but it's going to be u1 prime times y1 prime. So we have to take the derivative of what I had before. So that's a negative e to the negative x plus u2 prime times the derivative, so that will be negative 2 e to the negative 2x. And equals f of x, 1 over 1 plus e to the x. And from here, it's your choice which method to use, substitution or elimination. So what I'm going to do is, instead of using the matrix approach, which will take a little longer, I'm just going to use substitution of elimination here, because it looks like it's a lot easier, because the first term, it looks similar. One is positive, one is negative, which means all I have to do is just add the two equations together to make a zero out of those two terms. So we're going to take equation 2 and equation 1, we just literally add the terms together. So I get a 0 plus, if I add the middle terms, this is a positive 1 times this is a negative 2 times the rest, u2 prime e to the negative 2x. So if I add 1 to negative 2, I get minus 1, so I get negative u2 prime e to the negative 2x. The right hand side is just 0 plus 1 over 1 plus e to the x, just the way that whatever is there. Any questions? So I'm going to solve for u2 prime. I don't have to worry about the 0, so I'm going to divide by negative 1 and divide by e to the negative 2x. So u2 prime equals 1 over 1 plus e to the x. So when I divide by negative 1, it's just negative. So this negative goes to this side, it's still the negative. But when I divide by e to the negative 2x, it becomes multiplied by a reciprocal. So really just flip the negative sign, make it positive. So divide by e to the negative 2x, it becomes negative 1 over 1 plus e to the x times e to the positive 2x. That's when we divide by a negative exponential, which is negative e to the 2x divided by 1 plus e to the x. So be careful with the negatives in the, well, just general, be careful with negatives, right? Whether it's with the coefficients or in the exponent. And now we can solve for we can take the u2 prime, put it into the first equation, solve for u1 prime. So u1 prime e to the negative x plus u2 prime, I can plug in now, so that's a negative e to the 2x divided by 1 plus e to the x times e to the negative 2x is equal to 0. Which is really nice, because if you look at the numerator, you get e to the positive 2x, but multiply with e to the negative 2x. If you multiply those two parts together, I get just 1. But obviously there's a negative in front of it. So if you take this one and then multiply with this one, we just end up with a 1 at the end when we multiply. I don't mean. So we get u1 prime e to the negative x minus 1 over 1 plus e to the x equals 0. Move the fraction to the right-hand side, divide by e to the negative x. So I get u1 prime equals 1 over 1 plus e to the x. Divide by e to the negative x means multiply by e to the x. So I end up with e to the x, 1 plus e to the x. Any questions? But don't forget, we have to integrate, right? We don't need the derivatives of u1, u2. We have to know u1, u2. So let's integrate. So u1 equals integral e to the x, 1 plus e to the x dx. You probably know which technique to use, right, to integrate this, u substitution. I'm going to let you work out the process on your own. I'm just going to give you the answer. It's going to be natural log absolute value 1 plus e to the x. it turns out that there's no need to keep the absolute value sign for this. If we look at what we have here, the reason we have an absolute value because we want anything in the natural log to be positive, right? We cannot take a natural log of a negative. That's why we have this absolute value sign here. But then if you look at inside, e to the x is always positive, plus 1, so that means this sum is always greater than 1. So that's never going to be 0 or negative, so it's perfectly okay to drop the absolute value. So that's going to be natural log 1 plus e to the x. Since 1 plus e to the x greater than 1 for all x. And then we do the same thing with u2. So u2 is equal to integral e to the 2x 1 plus e to the x dx. And again, we might want to use u substitution by letting u equals 1 plus e to the x and carry out the steps. I'm going to do it really quickly. So that's going to be du equals e to the x dx. And then we can try to put into the integral. But first thing you have to do is that you have to, because here we have e to the 2x, we need e to the x dx. When I just split this numerator, the e to the 2x, we have to write it as e to the x times e to the x dx divided by 1 plus e to the x first. That way we can substitute for e to the x dx altogether with du. So that becomes, so this is u in the denominator, this is du. What about this e to the x? Well, that we can replace by rewriting this equation, u minus 1 equals e to the x. So we get u minus 1 over u du. And if we split that fraction, so we're integrating 1 minus 1 over u du, and then we end up with u minus natural log absolute value of u again. So plug in the substitute for u at the end, so we get 1 plus e to the x. I feel like I forgot the negative sign somewhere. Oh, I'm sorry. u2 prime is a negative e to the 2x. It doesn't change much. It's just going to be negative. So I'm going to bring the negative outside. My apologies. We get a negative here. So it's a negative 1 plus e to the x plus natural log 1 plus e to the x. Any questions? And now we're just going to take u1, u2, put into the particular solution. So yp equals u1, which is natural log 1 plus e to the x times y1 e to the negative x plus u2, which is a little bit long here. So that's going to be negative 1 plus e to the x. We can distribute the negative if we want, plus natural log 1 plus e to the x. And all multiply with y2 e to the negative x. Sorry, negative 2x. And then we can distribute the negative here, distribute e to the negative 2x if we want. But we can leave it for now. And then the general solution is going to be homogeneous, so c1 e to the negative x plus c2 e to the negative 2x. That's a homogeneous solution. Plus this particular solution, which is long. So I'm going to put it in there, and I'm going to distribute the negative, and I'm going to distribute e to the negative 2x into this bracket. So that will be natural log 1 plus e to the x times e to the negative x. We usually put it in front of the natural log. And then plus, so here I have negative 1 times e to the negative 2x. So that's minus e to the negative 2x. Then I have negative e to the x times e to the negative 2x. So negative e to the x times e to the negative 2x. Then I have positive natural log times e to the negative 2x. Any questions about what I did? There's quite a couple of distributions and rearranging the terms. Now the good thing about this is that this term, e to the x, e to the negative 2x, together give me e to the negative x, right? And that term is multiplied by negative 1. If we look at what we have here, we also have a constant times e to the negative x. It means that I can group those two together, so this term is being absorbed by this term. So I can group them together. I'm almost done here, I know we're running out of time. So we get c1 minus 1 times e to the negative x if I group them together. Same thing with the negative e to the negative 2x. That's a constant times e to the negative 2x. Here I also have a constant times e to the negative 2x. I can group those two together. So that will give me positive c2 minus 1 e to the negative 2x. And then the two natural logs, I can group them if I want to, or I can leave them. So I'll let you decide what to do with them. So plus e to the negative x natural log 1 plus e to the x plus e to the negative 2x natural log 1 plus e to the x. One last line before I let you go. So generally, we don't like to leave the coefficient as a subtraction or addition. We can just rename this as a new constant. And I'll be done. So that will be c1 hat. We can just put c1 hat or d1, so e to the negative x, plus c2 hat, e to the negative 2x, plus those two terms at the end. As you can see, even if we have full terms in a particular solution, right? But at the end, when we write down when we take the particular solution and put it into the general solution, two of the terms is actually absorbed by the homogeneous solution. So, anyway, I'll let you go. Sorry for, well, I guess I'm good. 5 o'clock. I'll see you on Thursday. Take care. Enjoy the spring. Are we in spring yet? Tomorrow, right? Tomorrow marks spring? March 23rd or 22nd? Tomorrow, right? Yeah. So officially, spring is here.